All right, let's dive into one of the absolute cornerstones of physics. Seriously, it's a concept you need to understand to describe, well, pretty much anything that moves, pushes, or pulls in the entire universe. We're talking about vectors. Let's get right into it. At its heart, physics is really just the rule book for how reality works. I mean, from the tiniest little atoms to the most massive galaxies, it's all governed by the same set of laws. And today, we're going to look at a super important part of that rule book, the vector. So let's kick things off with a simple problem, something to get our heads around this. Because you'll see, sometimes just knowing how much of something, it's just not enough. Not by a long shot. Okay, picture this. You've got a treasure map, right? You find the big red X, and you dig up a note. It says, the gold is 100 paces away. Awesome! But wait, 100 paces, which way? Do you go north, south, east? You're literally standing in the middle of a field, completely stuck. You're missing a critical piece of information.
And that missing piece, of course, is direction. Without direction, that number 100 is practically useless. And that right there is the fundamental problem that vectors were created to solve.
So in the world of physics, we really have two main ways of talking about quantities like this. It's time to meet our two main players for today, scalars and vectors.
And you know what? The difference between them is actually super simple. A scalar, it just has magnitude. Now, magnitude is just a fancy physics word for size or a number. It just tells you how much of something there is. But a vector, well, a vector has both magnitude and direction. It tells you how much and which way. So to really nail this down, just think of a scalar as a plain old number. That's it. Like the temperature outside is 25 degrees, or this bag of sugar weighs 2 kilograms. There's no direction to that, right? It's just a value.
But a vector, that's our treasure map instruction. It's the number plus the direction. So 100 paces, that's a scalar. Pretty useless. But 100 paces due north? Now we're talking. That's a vector. It's got the magnitude, 100 paces, and the direction, north.
Okay, let's make this way more concrete. I think the best way to see this difference in action is with a classic physics face-off, distance versus displacement. So let's imagine you're walking from your house, which we'll call point A, to a coffee shop at point B. Now, the actual path you take, down the sidewalk, around the corner, across the street, all of that adds up to your distance. That's a scalar. It's just a number. But the straight line, like a bird would fly, directly from your front door to the coffee shop, that's your displacement. And it's a vector because it has a distance and a direction. Right, so here's the key takeaway. Your car's odometer, it tracks distance. It's counting every single meter you drive. But displacement, that only cares about where you started and where you ended up. It's just your change in position. So think about it. You could go for a 5-mile run in a perfect circle and you end up right back on your couch. Your distance would be 5 miles, but your displacement, it would be 0 because you ended up exactly where you started. See how this stuff builds on itself? Now that we've got a handle on distance and displacement, we can up the stakes and talk about how fast something is moving. And this, naturally, brings us to another classic pair, speed versus velocity. And the connection here is just, well, it's perfect. Speed is the scalar here because it's based on distance, which is also a scalar. Your speedometer in your car, that's measuring speed. It just tells you how fast. But velocity is our vector. Why? Because it's based on displacement, our other vector. So velocity tells you how fast you're going and in what direction. 80 kilometers per hour is a speed. 80 kilometers per hour eastbound is a velocity. Okay, let's put this to the test with a quick thought experiment. This one's a classic. Imagine you're a runner on a standard 400-meter track. You run one perfect lap, and you finish at the exact same spot you started from. So, what can we say about your motion? Well, first up, the easy part. The distance you covered is, obviously, 400 meters. Your legs definitely feel those 400 meters. But because you ended up right back where you started, what's your displacement? Your overall change in position? It's 0. From a physics point of view, you haven't gone anywhere. And this is where it gets really cool. Since your distance was 400 meters, you definitely had an average speed, right? You were moving, but because your total displacement was 0, your average velocity for the whole lap was also 0. Isn't that wild?
You were running fast, but your average velocity was nothing. That is the power of thinking with vectors.
So you might be asking, okay, I get it, but why is this so important? Why do physicists care so much? Well, it's because in physics, direction is everything. It's the fundamental language we use to describe how things actually change in our universe.
I mean, check out this incredible chain reaction. We start with displacement, which we know is a vector. The rate of change of displacement, that gives us velocity, which is also a vector. And what about the rate of change of velocity? Well, that gives us acceleration, and you guessed it, it's a vector too. It's like a matryoshka doll of vectors. They just keep going.
Okay, and here's a concept that blows a lot of people's minds at first. Because velocity is a vector, it has two parts, magnitude, which is your speed, and direction. So you can change your velocity by changing either of those things. Speeding up or slowing down? Yep, that's acceleration. But what about just turning a corner? Even if your speedometer doesn't move one bit, the moment you turn that wheel, you are accelerating. Why? Because you changed your direction, which means you changed your velocity.
And look, this isn't just about running around a track or driving your car. These fundamental rules, these ideas built on vectors, they apply absolutely everywhere. It points to this incredible underlying unity in the universe. As this great quote from OpenStock says, galaxies are as immense as atoms are small, yet the same laws of physics describe both. Vectors are a huge part of that shared universal language.
Which kind of leads us to a final, pretty deep question to leave you with. In a universe where absolutely everything is constantly moving, planets are orbiting, galaxies are spinning, atoms are vibrating, can anything really be fully described by just a single number? Is a scalar by itself ever truly enough to tell the whole story? Something to chew on. Thanks for joining me for this breakdown.